In this seventh lecture on AC circuit, we shall continue our discussion on series LCR circuit fed by AC source. The circuit diagram is shown in the diagram. In the earlier class we have seen that dies out with time, and it is of the form of e to the power minus bt, where twice b is equal to r by l. The pi, the particular integral, survives, and current I, instantaneous current I, is given by v0 mod z e to the power minus j omega t plus phi, where the phi, tan phi, was defined to be like this: xl minus xc by r, that is the imaginary part of z by real part of z complex sample. And we know that for omega less than omega 0, phi is negative, and for omega greater than omega 0, phi is positive, and at omega is equal to omega 0, phi is negative. The variation of phase with frequency phi in rad, this is plus pi by 2 and this is minus pi by 2. As omega tends to 0, this part is omega L minus 1 by omega C by R. This tends to, as omega tends to 0, this tends to minus infinity, that is phi tends to minus pi by 2, and it is and when omega tends to infinity, it tends to plus infinity. Corresponding phi tends to minus pi by 2, and this phi tends to plus pi by 2. So this is the variation of phase with frequency. And now we come to the we have further defined the Q factor. We defined the resonance or response curve, the IRMS. IRMS was defined as VRMS by mod Z. This is equal to and the variation, the graph is the Lorentzian. We define this as the peak current Im, and in terms of RMS it is Im by root 2. This gives you the half power frequencies. Omega plus. Note that omega plus minus was obtained as b square minus omega 0 square plus minus b, and we define bandwidth and Q factor was defined as omega 0 by tau. The other key definitions of Q factor, we use Q factor is equal to omega tau, where at t is equal to tau, E tau is equal to 1 by E times E0, and we also defined is 2 pi times energy stored in the circuit divided by energy loss per cycle. And we also obtained another expression of Q factor is equal to 1 by R, root over LC. This much we have done in the earlier class. Now we shall first show the variation of reactances and impedances with impedance and also admittance with frequency. So the quantities which we are going to show the variation is XL is equal to omega L, XC is equal to 1 upon omega C, X is equal to XL minus XC, Z is equal, mod Z is equal to R square plus X square square root, and mod Y is equal to 1 by mod Z. All the quantities, this quantity has the dimension of mho, 1 over rho ohm, and all other quantities have the dimension of ohm. So we XL XC, it is rectangular hyperbola. They are equal at resonance. X and approaches this. This is X. Z and if we plot Y as a function of resonance, as a function of frequency, we see that it has a maximum at omega 0. So this is mod Y. And this curve is mod Z. So these are the variations. If we consider the energy stored in the inductor and capacitor, we know that the energy stored in an inductor is given by magnetic energy stored in inductor is half Li square. So this is half L. I is equal to V square by mod Z square, where I square we have written I star I. So it is basically V0 square. And the electrical energy stored in the capacitor is half CV square. So we write it half C, and for V square we write V0 Vc square, actually it is Vc square. So we write C, and Vc is equal to Xc times I. So this is minus J is there. So this is minus J I by omega C, and for I we write so the Vc square is V0 square omega square C square mod Z square. This is the expression for Vc square. And if we simplify this, this becomes half omega 0 square C mod Z square, and the numerator we have V0 square. So the total energy, total electrical and magnetic and combination of this is the magnetic energy and this is electrical energy. So this is half J V0 square, so it is V0 square. V0 square by mod Z square is common, and then we have 2 is common. Then we have L over here, and this is omega square C. This we write and we see that the total electromagnetic energy maximum of this is R square and this is 2 simply. So this is V0 square L by R square. This is L times I resonance, the current at resonance. V0 by R is the RMS current at resonance, and this is the N expression. Now we come to the voltages. We see that the current resonance occurs at omega is equal to omega 0. This is something like the amplitude resonance in force-damped oscillation. In force-damped oscillation, we also find that the velocity resonance occurs at some other frequencies. Similar cases may arise in LCR circuits too. So we shall consider the voltages across L, C and R, instantaneous voltage, VR, R times I. So this is equal to, you know that I is equal to V by mod Z e to the power J phi. And if we write explicitly, this is V0 e to the power J omega t minus J phi by mod Z. So this is V0 now voltage across inductor VL is equal to J XLI, which we write, we take this and VC similarly. If we consider the RMS currents, the RMS currents, so VRRMS is simply RV0 by mod Z. Similarly, VLRMS is equal to omega L V0 by mod Z, and VCRMS is equal to mod Z. Actually, we get the RMS values as first VRMS square is equal to 1 upon T V star V dt 0 to T. So the phase part goes, and we get this result. This is the current resonance. This leads to the current resonance. We have already started earlier. If we can consider this term, before going to the, if we want to see the variation of VC with frequency, then one thing is needed, that this derivative will be used. So this leads to then derivative of this now we take first V0 by C take out, this is the expression we have used. So this is omega square, and then we have 1 by C mod Z square minus, for this is not C, this should be omega, and for this we write this one, so this is 1 by omega mod Z cube, and then we have omega L minus 1 by omega C into L plus 1 by omega square C. We take minus V C omega squared mod Z cube common. So this term is mod Z square, and so this sign should be plus because minus has been taken common. This is mod Z square, and we have taken omega square common, so at 1 by omega, so 1 omega will be multiplied with it, so this will be, first term is as it is, this is this term, and if we multiply this with omega L plus 1 by omega C, so this is minus V0 square C omega square mod z cube. This part mod z square is r square plus omega L upon omega c whole square, and from this part we have omega square L square minus 1 upon omega square c square. If we expand it, we get minus V0 C omega square mod z cube, and within bracket this is r square. Then this term will be added to twice omega square L square, and the cross term this is there. Now we take L out. So for Vc to be a maximum, this has to be 0. For Vc on Ms to be maximum, r square plus twice omega c square L square minus twice LC has to be 0. This subscript C means it is the frequency at which Vc max appears. This gives you this part is omega 0 square minus, you see the Q factor, R square L square C square. We have multiplied the all through we have missed this. This is the term that creates difficulty. We have divided all through by 2 and this was missing. So this is omega 0 square and this is twice b square. You know that twice b is equal to r by L. So this is r square by L square, this is twice b square. If we take omega square common, omega 0 square common, this is 1 minus twice b square by omega 0 square, and Q factor is defined as omega 0 by twice b. So omega 0 by twice b, so this is equal to omega 0 square 1 up 2q square. So we see that the resonance of Vc appears at a value less than the resonance frequency. So this maximum occurs at omega 0. The maxima of this occurs at omega is equal to omega 0. The maxima of this occurs at omega c is equal to omega 0 square root over 1 minus 1 upon 2q square. Now we come to the variation of volt RMS voltage across L with frequency. So dVLRMS d omega, we use this expression, so we take the V0L out, so this is dd omega of omega by mod z. So this is V0L 1 by mod z minus omega by mod z square d mod z d omega. So V0L 1 by mod z, then this part is omega by mod z cube this is omega mod square, and there is another term, and then it follows by omega L minus 1 by omega C into L plus omega square C. Now if we multiply this and we take z cube common, V0L mod z cube common, so this is mod z square minus this omega is multiplied with this, so omega L minus 1 upon omega C into omega L plus 1 by omega C. This is V0L by mod z cube, then from this part R square plus omega square L square plus 1 upon omega square C square minus twice L by C. This square part is this, and this is minus omega square L square plus 1 upon omega square C square. So this part goes. R square plus 2 omega square C square minus 2 by LC. Now for VLRMS to be a maximum, one must have the quantity within the bracket 0, that is we have R square plus twice omega square C square. This is called omega L because it is the value at which the maximum of VL occurs is equal to 0. Or we write R square by 2. Further, 1 upon omega L square we multiply by so this is LC minus C square R square by 2. This is 1 by omega 0 square and C square R square. C square R square can be connected to C square R square can become, so we take first LC common, so this is 1 minus CR square by 2L. This part is omega 0 square, 1 upon omega 0 square, this is 1 minus as Q is equal to 1 by R root over L by C. So this is, we can approximate at omega L is equal to omega 0 times 1 minus 1 by 2q square to the power minus half. If we consider Q to be high, then this is for high Q. For low Q, no, this result is not valid. But whatever may be the result, it is found that omega L is greater than omega L is greater than omega 0. And sorry, and this resonance occurs at omega L greater than omega 0. So if we plot the variation of RMS voltages, we see the RMS voltage first. If we consider VC, the variation of VC is like this. This is VC. The variation of VL is like this. VL, all are the RMS voltages. VL, and this is the this is VR, and this is the value where this maxima occurs is omega C. This maxima occurs at omega 0, and this maxima occurs at omega L. These are the graphs, and we see that if we measure the current current or voltages across the resistance, it acts as a high band pass filter. Only the frequency in the neighborhood of the of omega 0 has a good response. This part VC if we measure the voltage across capacitor, it acts as a low pass filter, and if we measure the voltage across VL, it acts as a high pass filter. The most interesting thing is that at the resonance, VL and VC are same. Sometimes it is found that for a circuits having low Q, the resonance curve becomes a flat one, so that when you measure the VR, there is no appreciable change of VR over a range of frequency. So it becomes very difficult to identify the resonance frequency. In that case, it is the relative magnitude of VL and VC will have. For near, this discussion is valid near resonance. For omega less than omega 0, VC is greater than VL, So relative measurements of the RMS voltages, if you find that Vc is higher than VL, then we are the frequency is lower than resonance frequency. For omega greater than omega 0, Vc is less than VL, and at omega is equal to omega 0, Vc is equal to VL. In practice, this exact equality may not be obtained, so these two would be approximately equal. That will help you in determining the exact resonance position. And if we define the current gains may be defined as usual in terms of RMS values, and other things can be defined similarly. The current gains will have the similar behavior. That's all with series resonance circuit. In the next class we shall consider parallel resonance circuit, that is when all the three components are connected in parallel. And finally we will end the discussion on LC circuit by discussing what is known as rejector circuit. This circuit is called acceptor circuit because it accepts the frequency range in the neighborhood of the resonance frequency and rejects all which are lying away from resonance frequency. In the rejector circuit, the reverse thing happens, as we shall see that only the frequency in the neighborhood of the resonance frequency are being rejected. That is, at these frequencies the current is low and the current rises up for frequencies away from the resonance frequency.